Here's a periodic table from the University of Nottingham. And if you go to their site, if you pick any one of these elements, you get a chance to see a description of it. The one I'm choosing here is phosphorus, and I'm going to take a short clip showing white phosphorus burning because it's an exothermic reaction. If you want to see the entire video, go to their site and click on phosphorus. They give you quite a bit of information on it, but let's watch this phosphorus burn. And it gets heated, and whoosh, you get this light, you get this heat. It's a beautiful reaction, a deadly one, though, too. I picked this problem because even though it's relatively simple in terms of moles and enthalpy, it has a nasty twist to it that you see every once in a while in some FRQs. So let's go over this. This is a good stoichiometry problem, and also it relates to the enthalpy of reactions. So here we go. You've already seen that phosphorus burns beautifully, and in this problem, we have white phosphorus, dangerous substance. It was one of the first industrial elements to be banned in 1912 because of it was being used in making matches, and it was quite toxic, and it was maiming and killing many people. So there was an international agreement to stop making matches with white phosphorus. Right now, matches have red phosphorus, which doesn't have the same biological action as this P4 molecule. Very interesting. It's got strained bonds here, forming this beautiful tetrahedron. Anyway, it burns with oxygen, and here's our tetraphosphorus decaoxide or decoxide, a molecular substance, so we've got those prefixes. Okay, now here's the reaction. P4, you wouldn't have to memorize that this is a tetraatomic substance. You'd be told that in the reaction. P4 reacting one of the several forms of phosphorus, reacting with our diatomic oxygen, which you have to know. And here's the balanced reaction, making that white solid. And the change in enthalpy, the change in the stored energy of phosphorus and oxygen, pretty high amounts of stored energy, to P4O10 is a drop of negative 3,013. That's a lot of kilojoules per mole of this reaction, and we'll get back to that later. This mole of reaction is what's has been showing up on exams every once in a while, so it's worth knowing. Okay, first of all, calculate the change in enthalpy, not when we have this reaction, but when 309, calculate the change in enthalpy with 309.7 grams of white phosphorus, and again, they remind you that this is tetraatomic, completely burns in air according to this equation. That's a lot of phosphorus. In fact, I had a chance to meet a computer programmer who had about this amount, and it blew up on him when he was a kid, and he lost a hand and an eye and didn't go on in chemistry. So here we go. We have 309.7 grams of this stuff, and grams, come on, we're going to change it to moles. So the first thing I'll do is I'll pull up my calculator, and I've got the white phosphorus, and the molar mass of white phosphorus is 30.97 grams per mole. It's underneath nitrogen. It's in the nitrogen family. And we have to multiply that by 4 because these molecules are tetraatomic. I'll get that answer, and that's going to be the molar mass of our P4, so that's going to be an important value, and I'm going to store it as X. You should learn how to store a value on your calculator. So that's it. X is going to be the molar mass of P4. And I've got 309.7 grams of this stuff. Like I said, a significant amount. I wouldn't play with that amount. I wouldn't play with anything larger than a grain of rice. And this stuff is very, very toxic on top of it all. So we divide by our molar mass, which I had as X, and then we're going to multiply that by how much we get per 1 mole. Oh, well, wait, let's divide it by X and see how many moles we've got. We've got 2.5 moles. Yeah, okay. We've got significantly more than a mole. Our 120, yeah, this is 300, 2.5 moles of P4. And so we're going to have to take our negative 3,013 kilojoules and multiply by that 2.5 moles and get our answer, 7,533. If I kept it to 4 sig digs, I'd have it as that. But I'm going to round this off to the nearest tens. Keeping track of that much heat is very, very difficult. And I'll just put that in there. Let me pull up my calculator again, make sure I put the right value in. Yeah, negative 7,530. You could have put down to 3 and it would be valid. That's a lot of kilojoules. We're talking about actually megajoules in this case of energy. And so we've taken very reactive substances and made a less reactive substance our final product. We've lost that energy, given it to the surroundings. So these are the ashes. So fine, if you take 309.7 grams and burn it with enough oxygen, that's how much heat you're going to end up getting. Heat and light energy, both together. Now, calculate the enthalpy change when 309.7 grams of phosphorus is not burned with enough oxygen. It's burned with only 56 liters of oxygen at standard temperature and pressure. So we have got an amount of phosphorus. We already figured that out, 2.5 moles of phosphorus. And we remember that from the previous thing. And we don't know how much oxygen we have here, but this STP, that's very forgiving. It's something that you should remember. When somebody gives a gas at standard temperature and pressure, you probably should go to your memory banks and remember the value, but I'm going to go directly to our Chem Advantage site, and underneath resources, I'm going to go quickly to the equation sheets, and you'll find on the equation sheet that down here with gases, there's a value that says an ideal gas at STP has 22.4 liters per mole. You should remember that. It's easy to remember, 22.4, about a basketball size or wastepaper basket size worth of gas. That is what 1 mole of gas is at standard temperature, a chilly 0 degrees Celsius and 1 atmosphere of pressure. So let's go back to our value here and say, okay, 56 liters, and we know that there are 22.4 liters in a mole, and 22.4 liters divided into 56.0 liters of oxygen at STP, we're dealing with a gas, is going to be 2.5 moles of oxygen. I set this experiment up on purpose to do that. But, you're given a volume of a gas, STP, divided by 22.4, and you've got moles. I mean, we always know we need moles, so that's pretty good. So we know we have 2.5 moles of oxygen that we're going to be dealing with. And so we have an equal amount of phosphorus and oxygen. Now, which is the limiting reactant, or do we have a stoichiometric amount? Well, let's look at the balanced reaction. That's what I've got here. Here we've got our balanced reaction, and 2.5 moles of phosphorus, 5 moles of oxygen. Now, for 5 moles of oxygen, when you have 2.5 moles of phosphorus, you're going to need 5 times more oxygen. So oxygen is what we're running out of. Remember, if you wanted to quickly find out what the limiting reactant is, divide your mole amounts by the coefficients. Okay, we divide this mole amount by a coefficient, we still get 2.5. We divide this by 5, we get 0.5. So that is our lower value. Without doubt, oxygen is going to be our limiting reactant. All right. Very often, on a limiting reactant problem, they will give you 1 point if you find the moles of the both reactants, and they'll give you another 1 point if you determine the limiting reactant and give a rationale for it. You can say, I'm going to run out of this, or just show dividing by 5. Or only say, okay, so now, in this reaction, we will end up having 2.5 moles of oxygen react with 0.5 moles of phosphorus, because the extra phosphorus is just going to be lying around there. It doesn't have enough oxygen to react with. Now, this is where the tricky part is, and this is why I've got this video. This is what 95% students get wrong on this type of a problem. Use the moles of the limiting reactant stoichiometry to find out how much enthalpy change we have for this. Now, the moles of oxygen that reacted were 2.5 moles. When they give you the enthalpy of a reaction, AP says it is per mole of reaction. And when they say that, they say use the coefficients. You will get this heat when 1 mole of phosphorus reacts with 5 moles of oxygen. So this heat's produced, this negative 3013 is for 5 moles of oxygen. And that's what is tricky with people. So on this ratio, I say I have 2.5 moles reacted, and 5 moles will make 3,113 kilojoules. But we only have 2.5. So you could figure out we're going to get half this amount of heat. This is a nice way of setting up in terms of ratios, or you could have set up a ratio saying 5 is to negative 3,113 as 2.5 is to x. And your answer is going to be, in this case, we'll have to take our 2.5. We're going to have to take our 0.5, which is the result of 5, into this, and multiply it times our kilojoules. I get my little calculator, and I'll get back to my negative 3015, and divide it by, I'll do it the long way, divide it by 5 times 2.5, and we should get about, again, half that value, and there it is. We can just end up saying the final answer for this is going to be negative 1507 or negative 1510, which is where I'll type in here, negative half of this, 1,500, and let me just remember that last number. I checked back my calculator, and 10, and don't forget your units, kilojoules. When you, kilojoules. When you burn 2.5 moles of oxygen with 0.5 moles of phosphorus, that's the heat. About 1.5 megajoules of energy will be released to the surroundings because the chemicals have lost that potential energy. All right, so whenever you have a problem where there's moles of reaction, remember this is how it's set up. And if you're given a certain number of moles of material, you're going to have to compare with that. Okay, that's this problem, enthalpy and stoichiometry.